Right. More awesome cuts from this album. Okay, that's my motivation song for you folks. Work it harder, faster, better, stronger. Maybe not faster, but work harder. Okay, I know you folks are working real hard for me, and I appreciate that. So let's keep it going. Okay, so rules for writing covalent and polar covalent Lewis structures. Fantastic. We're going to get into it. So I got some rules here for you. I'm going to go through these briefly, and then I'm going to show you how we apply them. Okay? Sorry, I'm making sure I got a stopwatch going so I don't talk too long. Okay, so first, rule number one, sum the valence electrons from all the atoms. Don't worry about which has which. Just add them all up, okay? And so I'm going to go through examples of this. So we'll see examples of how to do it. So add up all the valence electrons, okay? And keep track of what the sum. Keep track of that sum. So then we use a pair of electrons to form a bond between each pair of bound atoms. Okay, great. And that pair of electrons we're going to use from our sum. So that sum that we come up with, we're going to distribute all those electrons around. All right. Every time we want to make a bond, we have to use two of those electrons. The atom with the greatest bonding capacity is the central atom. Okay, so what does that mean? So bonding capacity, let me back up here and go to this figure, okay? These are really related to bonding capacity, okay? So in other words, if I look at something like neon, neon has no bonding capacity whatsoever. It has the octet rule, okay? But now if let's say I was comparing carbon and fluorine. Carbon has a lot more bonding capacity than does fluorine. So carbon only has 4 valence electrons. It can take 4 more, okay? Fluorine has 7 valence electrons. It can only take 1 more. So carbon has the larger bonding capacity than fluorine, okay? And so that is the atom that's going to make the central atom. Whichever one in the pair, right, when you're making your molecule with your Lewis structure, the one with the greatest bonding capacity will be the central atom. So we arrange the remaining electrons from our sum around everything to satisfy the duet rule for hydrogen and the octet rule for second row elements. So for now, let's just say for everything else, as lone pairs. Okay. And then Clark's rule for multiple bonds. So we'll get there soon. So for now, this is just the simple Lewis structures. Okay. But we're going to build upon these simple Lewis structures to get into the more complicated ones. So for now, we're just going to look at rules 1 through 4. All right. Okay, so let's apply it. So draw Lewis structures for the following molecules. So the first one we're going to do is methane. Okay. And I will walk you through this example of how I get it. All right. And then for the other ones, I'm going to put the tunes on and I'll work through it with some music going on, and you could pause it and work on it on your own or work along with me. So with methane, we recognize that carbon, 1, 2, 3, 4, carbon has 4 valence electrons, and each hydrogen has 1 times 4, right? So I get 8 total electrons, 4 plus 4 to give me 8, okay? I recognize carbon has the bigger bonding capacity than hydrogen. And at first you might think, well, hydrogen only has 1 and carbon has 4, but we have to remember hydrogen can only take 2 electrons. So hydrogen's almost never, 99.99% of the time, hydrogen is not going to be the central atom, okay? But carbon almost all the time makes the central atom because carbon has a lot of bonding capacity. So I'm going to put carbon in the middle as a central atom. And I have 4 hydrogens and I'm going to surround it, okay? So I'm going to say hydrogen, 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 hydrogen. I'm going to draw the bond between each one. And now I need to count up all of my electrons to make sure I use them all. So remember, I had 8 that I have to use. And check it out. 2, 4, 6, 8. So there we go. We used all 8 of them. Now we have to check that we've satisfied the octet rule. So carbon wants to have 8 electrons surrounding it, and indeed it does. 2, 4, 6, 8. Hydrogen wants to have the duet rule. So each hydrogen can only have 2 electrons in it. And so this hydrogen, right, is only, no lone pairs, which is correct. So this hydrogen is sharing 2 electrons with this carbon. So this hydrogen has 2. This hydrogen has 2. This hydrogen has 2. This hydrogen has 2. Fantastic. This is my Lewis structure for methane. So this one, you can see no lone pairs. It's very simple. No dipole moment because it's totally symmetrical. And I think I forgot to say that on the previous slide. So I'm going to make that note right here. Okay. So this SF6, it's symmetrical. And that's a good indication of no dipole moment when a molecule is symmetrical. Okay. So now let's do the other ones. I'm going to bring the tunage back on. I'm going to turn it down just a little bit. Okay, let's do it. Okay, let's work on CF4. Okay. 2, 4, 6, 8. Okay. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Great. Okay. And each fluorine is 2, 4, 6, 8. Octet rule. Carbon is 2, 4, 6, 8. Octet rule. Okay. Two. 2, 4, 6. Great. That's it. So 1 electron for hydrogen, and there's 2. 1, 2, 3, 4, 5, 6 for oxygen. Okay. 2, 4 from the bond. plus 2, 4 equals 8. Okay, so hopefully you're able to follow along with these examples. These are all the simple examples. Okay, we could come up with a lot more simple examples. And what's also important to note, when we're doing Lewis structure, we're not necessarily concerned with getting the correct angles. We just kind of draw everything around the central atom evenly. Okay, so we'll see water is actually not shaped like this, and we'll see why that is. Okay, so hopefully all these examples made good sense and you're able to arrive at these examples. Okay, so let's move on. So now let's get into Clark's rule. And Clark's rule is going to give us the rule for when we have multiple bonds. So that means double bonds or even triple bonds. So Tom Clark, so this is a cool story. Tom Clark was professor of chemistry at HSU. He won the Outstanding Professor of the Year in 1981 and 1982, so a long time ago. And this rule is not just like an HSU thing. This is a really famous rule that's widely published throughout chemistry texts. It just so happens to not be in our textbook. So this is a bit, older. It's an older rule, but I still think it works great. So that's why I'm kind of diverting from the book a little bit and giving some credence to Professor Clark for his rule. 6y plus 2 equals x. That's the equation he came up with. So what does this equation mean? So in this, y are all non-hydrogen atoms. Okay? X is this number to be compared with to the total number of valence electrons. All right? And I'm going to work through some examples. It's kind of an obscure looking equation. The math is obviously simple, but we'll work through some examples to see what this does. Okay? So if we do this calculation, 6y plus 2, okay, where y is the number, I'll say the number of all non-hydrogen atoms, okay? So if it's 1, it becomes 6 times 1 plus 2 equals 8. If there's 2 of them, it becomes 6 times 2 plus 12 equals 14, and so on, okay? If this number x that we get from this equation equals the number of valence electrons, then we're good to go, and it's all single bonds, okay? So for example, let's back up here, okay, and I'll put in 6y plus 2. So let's do this for water. So this number y, remember, is all non-hydrogen atoms. So that's only 1 for oxygen, right? So that's 6 times 1 plus 2, and that equals 8. That number 8, that equals the number of valence electrons. So we're good. We got the right Lewis structure. All single bonds, we're good to go. Okay? What about CH4? All right? Well, that's 5 non-hydrogen atoms, right? 1 for carbon, 4 fluorines, so 5. So, and maybe you can see already that this is going to work really well. 6 times 5 plus 2 is 32. 32 and 32, that's the right structure, right? All single bonds, okay? And we could do the same for methane and HF, and it would work out. And you should prove that to yourself, okay? So, what if X does not equal the number of valence electrons? Okay, well, this is where this rule is very useful. So if X is greater than the number of electrons, then that means we need double bonds. And there's a really nice pattern with this. If X is greater than the number of valence electrons by 2, then that means we need 1 double bond. If X is greater than the number of valence electrons by 4, then we either need 2 double bonds or 1 triple bond. And so forth, as we could keep imagining, right? If X is greater than valence electrons by 6, that could be 3 double bonds or 2 triple bonds, etc. Okay? So now, if X is less than the number of valence electrons, then the central atom has what we call an expanded valency. And so what that means is it violates the octet rule. And by expanded valency, what I mean is it's Texas-sized. These are Texas-sized molecules. So that's my little joke, because everything is big in Texas. So in other words, if X is less than the number of valence electrons, it could have 10 electrons surrounding it, or 12 even, okay? So it's a Texas-sized valence electron, okay? Because everything is big in Texas. Any of you from Texas to get that joke? Maybe you can give me some love in the comments. Okay, so let's do some examples, all right? And what I'm going to do, so you can have the option of working alongside me if you want. I'm going to do one. I'll do the CO2, and then I'll do the other three. And you should work alongside me or pause it and work on it your own and see if you come up with the same answer that I do. So let's first do CO2 together. So carbon has 4 valence electrons, 1, 2, 3, 4. Oxygen has 6, 1, 2, 3, 4, 5, 6. And there's 2 of them. So 4 plus 2 times 6 gives me 16. So that's the first thing I need to do is count up the total number of valence electrons. Now I'm going to do the 6y plus 2 rule, the Clark's rule. Okay. So there's 3 atoms in this molecule, and none of them are hydrogen. So I can say 6 times 3 plus 2, aha, and that gives me 20. Okay. And because there is a difference of 4, that's going to either equal 1 triple or 2 doubles. And we actually have to make a logical decision on what it should be. So the first thing I'm going to do is recognize carbon is definitely the central atom because carbon has more bonding capacity than oxygen. Okay? And I'm going to surround it with oxygens. And I'm going to put a bond here and a bond here. And let's just stare at this thing for a minute, okay? And as you look at this, hopefully you can arrive at the conclusion that it's got to be 2 double bonds, because why the hell would one of these be a triple and the other would be a single, right? That's contrary to what these atoms and molecules want to do. They want to spread themselves out where they can, okay? So if you've got 2 identical atoms, like 2 oxygens on the other side, and it's this situation where it's 1 triple or 2 doubles, it's always going to be 2 doubles because the atoms want to spread around. The electrons want to spread around. So that's going to be 2 double bonds, okay? And so now if I count up how many I've used 2, 4, 6, 8. So I've used 8 of my 16. So remember, 20 doesn't give me the number of valence electrons. It's just this number that I use on Clark's rule to compare, okay? So I've used 8 of the 16, so I've got to distribute 8 more around this thing. And I also remember that I'm doing the octet rule. I have to satisfy the octet rule. So if I look at carbon, carbon has 2, 4, 6, 8. So carbon is good to go. Carbon is already surrounded by 8 electrons. But what about each oxygen? Well, each oxygen is only surrounded by 2, 4. Even though they're sharing, and they're not sharing equally, right, because oxygen is more electronegative than carbon, even so, oxygen only has 4 electrons. So I need to put another 4 electrons, and we just kind of spread them around like that. So now this oxygen has 2, 4, 6, 8. This oxygen will have 2, 4, 6, 8. Okay, that gives me 8 and 8. 8 plus 8 equals 16. So I've used all 16 of my valence electrons. And here's my Lewis structure for carbon dioxide, 2 double bonds. Okay, so I'm going to play the music. And if you want to work alongside with me, you can. If not, if you prefer to pause it, do it on your own and then see how you do. You can do it that way as well. All right, let's go for it. Let's see. I'm going to skip tracks too. Let's see what we got. Let me find one I like. Ooh, wait, hold on. I'm going to go back. Now I'm just messing around and wasting time. I think I played that one already. What do I want? I can't decide. Let's go back to this harder, better, faster, stronger. Because that's how you're going to finish out this semester, right? Okay. Okay. Nitrogen. Let's do it. 1, 2, 3, 4, 5. Right? Because how do I make two doubles? I can't. 2, 4, 6. 8, 10. Right? A cation means it's one electron removed. Like this example. Okay, so if it's an ion, whether it's a cation or an anion, we still put the brackets around and indicate that it's an ion. Okay, the negative charge adds an electron. Another 14. Okay, beautiful. So, as you can see, all of these examples, two atom examples, when you put two non-hydrogen atoms into that Clark's rule, you're always going to get 14. So that's another really quick thing to recognize, right? Whenever you have two atoms in a molecule, Clark's rule is always going to give you 14. So you got to add up those valence electrons to see where it takes you. When we have a cation, it takes away an electron. And in covalent molecules, okay, whether it's a cation or anion, we still put it in brackets and put the charge. If we have an anion, it adds a charge, okay? And once again, we still put it in brackets and put that charge on there. Everything has the octet rule satisfied, so every atom has 8 electrons surrounding it. And if I were to go and count these up, I've used, you can see for all of these structures, right, 10 electrons each time, because each one of these molecules into cyanide and the nitrogen monoxide cation, they all have 10 electrons, okay? So that's pretty cool. All right, moving along. Okay, exceptions to the octet rule. So that's what we're gonna get in next. Let's see how we're doing on time. I think I'm gonna make this a separate video just to keep us, just to keep your brains from swelling with too much knowledge. Okay, folks, I will see you in the next video.